Good morning everyone. I am Garima from BSc Chemistry Honors first year. Today we are going to start our chapter 4, that is Alkenes and Cycloalkenes of Organic Chemistry. Introduction. The simplest organic compounds are hydrocarbons, the compounds containing only carbon and hydrogen, depending upon the framework of carbon atom in its molecule. The hydrocarbons may have either open chain or ring structure. In addition, they may be saturated or unsaturated in character according to the nature of carbon-carbon bond in them. Due to these variation, hydrocarbons have been divided into different classes. We shall discuss the various classes of hydrocarbon one by one, starting with the alkanes and cycloalkanes. Structure of alkanes. Alkanes are open chain saturated hydrocarbons having the general formula CnH2n plus 2, where N is the number of carbon atoms. They contains only single covalent bond between carbon and carbon and hydrogen in their molecules. As such, each carbon atom is bonded to four other atoms, as is clear from the formula of methane, ethane and propane, the first three members of alkane. The bond in alkanes are formed by the overlapping of sp3 hybridized orbital of each carbon atom with similar orbitals of other carbon atom or 1s orbital of hydrogen atom. As a result, all the four bonds linking the carbon atom with other atom are sigma bond. As these bonds are quite strong and are not easily attracted by other reagents, alkane do not react with the usual laboratory reagents under ordinary condition. That is why they are termed as saturated hydrocarbons or paraffins. Latin word param means little, affins means affinity. It may also be noted that due to sp3 hybridization of the carbon atom of alkanes, the four bonding orbitals of each carbon are directly towards the four corners of tetrahedron. For instance, let us consider the case of methane, the simplest alkane. In the formation of its molecule, the four sp3 orbital of the only carbon atom overlap the 1s orbital of the four hydrogen atom, which are situated at the corners of tetrahedron as shown in figure 4.1a. Figure 4.1b represent a molecular model of methane. Figure 4.1c is a simplified three-dimensional representation of the molecule. In this representation, the wedge represent the bond pointing towards the observer out of the plane of the paper. The hatched line represent the bond going away from the observer behind the plane of the paper, and normal line shows the bond in the plane of the paper. Each carbon-hydrogen bond has the length of 110 picometer or 1.10 angstrom, and each HCH angle is 109 degree 28 second. Figure 4.1d. So all these are explained in figure 4.1 that shows the formation and structure of methane. Similarly, in case of ethane, figure 4.2 and higher alkane, the relative arrangement of bonds is always tetrahedral, although the different bond angles may be slightly different from the regular tetrahedral value of 109 degree 28 second. The carbon hydrogen bond length is about 110 picometer 1.10 angstrom, while the carbon-carbon bond length is 154 picometer 1.54 angstrom, or nearly so. This figure shows the molecule of ethane. On account of the tetrahedral arrangement of four bonds formed by each carbon atom, the molecule of alkane are three-dimensional in nature. Moreover, in case of alkane containing more than two carbon atoms, the carbon atom of the chain do not actually lies along a straight line. This is quite obvious from the model of propane shown in figure 4.3. In fact, for higher alkane, the carbon-carbon chain can assume a variety of zigzag shapes, but for the sake of convenience, the carbon atoms are written in the straight line as so far as possible to have a planar representation as shown below. Figure 4.3 shows the molecular model of propane, showing that the carbon Here the figure 4.3 shows the molecular model of propane, showing that the carbon atom does not lie along a straight line. Classification of carbon atom in alkane. The carbon atom present in alkane can be divided into four categories as shown below. First, primary carbon atom. It is the carbon atom which is linked directly to either one or no carbon atom. Secondary carbon atom. It is the carbon atom which is linked directly to two carbon atom. Tertiary carbon atom. It is the carbon atom which is linked directly to three carbon atom. Quaternary carbon atom. It is the carbon atom which is linked directly to four carbon atom. For example, in the formula given below, there are 5 primary, 1 secondary, 1 tertiary and 1 quaternary carbon atom. Hydrogen atoms are also classified as primary, secondary and tertiary accordingly as they are linked to a primary, secondary and tertiary carbon atom respectively. Thus, in the example given above, there are 15 primary hydrogens, 3 each on the 5CH3 group, 2 secondary hydrogen on the CH2 group and 1 tertiary hydrogen on the CH group. Nomenclature of alkane. The common and IUPAC name of saturated hydrocarbon are discussed below. The common system. According to this system, the first 4 members of saturated hydrocarbon have special name, while the higher members are named according to Latin or Greek numeral indicating the number of carbon atom in the molecule. The name of all the members and is in ane. Thus, these are the names and formulas of some of the molecules. In case of isomeric alkane from C4H10 onwards, the following distinctions are made in naming the various isomers. First, the hydrocarbon having all the carbon atom in a straight or continuous chain are termed normal or N-hydrocarbon. For example, CH3, CH2, CH2, CH3 is called N-butane, while CH3, CH2, 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 CH3 is named N-pentane. Second, branched chain isomer having a tertiary carbon atom are known as iso, while those containing a quaternary carbon atom are known as neo. For example, isobutane, isopentane and neopentane. Alkyl groups. The removal of one hydrogen atom from a molecule of an alkane gives a monovalent group called alkyl group. It has the general formula CnH2n plus 1 and is usually represented by the letter R. The name of alkyl groups are obtained by replacing the suffix "ane" of the name of corresponding alkane by "yl". It may be possible to get more than one alkyl group from an alkane depending upon the position of carbon from which hydrogen is removed as illustrated below. Name and formula of alkane: methane, ethane, propane, N-butane, isobutane. Formula, name and abbreviation of alkyl group: methyl, ethyl, N-propyl, isopropyl, N-butyl, secondary butyl, isobutyl. Similarly, isobutane has the name and abbreviation as tert-butyl. IUPAC system. Straight chain alkane. The alkane in which all the carbon atoms are present in a straight chain are named by adding the suffix "ane" to the appropriate word root. For example, methane, ethane, propane, butane. Branched chain alkane. In case of branched chain alkane, the largest possible continuous chain of carbon atom is selected, the corresponding word root followed by the suffix "-n" is written down. The chain is numbered from the end, which gives the lowest number to the carbon carrying the substituent alkyl group. If the number of substituent groups is more than one, number is done from the end according to lower set of locant from the branching alkyl group. The names of branching alkyl group along with their branchment numbers are then prefixed before the word root in alphabetical order as illustrated below. 2-methylpropane, 2-methylbutane, 2,2-dimethylpropane, 4-ethyl 2,2-dimethylhexane, 4-ethyl 3,6-dimethyloctane. Some important points for giving IUPAC name. A few important points to be remembered for IUPAC name of alkene are given below. First, if two different alkane groups are equidistant from the two ends of the parent chain, the numbering of the chain is done in such a way that the group which come first in alphabetical order get the lowest number. For example, 3-ethyl 6-methyloctane. Since ethyl comes ahead of methyl in alphabetical order, the parent chain is numbered from the end, which gives lowest number to ethyl group. If the group attached to the parent chain is also branched, sometimes called complex substituent, it is named as substituted alkyl group by separating numbering the carbon atom of this group. For this purpose, the carbon atom of this group which is attached to the parent chain is always numbered as 1. The name of such group is always written in bracket. For example, N-ethyl 2-methyl 5 bracket 2-methylpropyl bracket close nonane. Third, for deciding their alphabetical order, the complete name of the complex substituent including the prefix as di and tri forming the part of the name is considered. For example, 5 bracket 1,2 dimethylbutyl bracket close 7-ethyl 2-methyldecane. The alphabetical order of the name of the complex substituents is decided on the basis of letter D, which is the first letter of the complete name of this group. Fourth, while naming a compound, if two equally long chain are possible but the number of side chain attached to each possible chain are different, the possible chain having larger number of the side chain is selected as the parent chain. For example, 3,5-diethyl 2,4-dimethyloctane, correct parent chain since it has 4 side chains. The second one is incorrect parent chain since it has only 3 side groups. Structural isomer in alkane. Each of the first 3 members of alkane, methane, ethane and propane, can have only one structural formula, that is as shown in the figure. However, the higher members from butane onward can be represented by more than one structural formula and thus exhibit structural isomerism. The various isomerism of the same hydrocarbon differ in the framework of the chain of carbon atom, and therefore isomerism exhibit by alkane is termed chain isomerism. For example, butane exhibits in the form of 2 isomers as shown below, N-butane and isobutane. Similarly, pentane exhibit in the form of 3 isomers, that is N-pentane, isopentane, neopentane. C6H14 exists in the form of 5 isomers. C7H16 have 9 isomers and C8H18 have 18 isomers, and so on. Problem 4.1. C6H14 exists in the form of 5 isomers. C7H16 have 9 isomers and C8H18 have 18 isomers, and so on. Natural source of alkanes. Petroleum, which occurs naturally below the surface of Earth is a mixture of many hydrocarbons, most of which belong to alkane series. Natural gas, which issue from petroleum field, and fuel gas obtained from coal, contain lower alkane. The waxy constituent of some plants have also been found to contain alkane. For example, pine wood and turpentine oil contain N-hexane, while the leaves of cabbage contain nonane and non-cosane C29H60. General method of preparation. The preparation of alkane by synthetic method is only rarely carried out. The usual practice is to isolate these hydrocarbons, particularly the lower one, from some suitable natural sources. However, some of the general methods which can be employed for their preparation are discussed below. First, hydrogenation of unsaturated hydrocarbon. Sabatiers and Sanderin reaction. Alkene or alkynes can react with hydrogen in the presence of catalyst, finely divided nickel, platinum or palladium to form alkene, as shown in this. The use of nickel as a catalyst for hydrogenation requires temperature of about 525 to 575 Kelvin. But if platinum or palladium is used as catalyst, the reaction can take place even at room temperature. Methane cannot be prepared by this method, as the starting alkene or alkyne must contain at least 2 carbon atoms. Reduction of alkyl halide. Alkyl halide can be reduced directly or through the formation of Grignard reagent to form alkane. Direct reduction. The direct reduction of alkyl halide is generally carried out with chemical reducing agents such as zinc and hydrochloric acid, or zinc copper couple, and alcohol, or with hydrogen in the presence of palladium catalyst. Alkyl halide in the presence of zinc and H positive will give alkane. N-butyl bromide in the presence of zinc and H positive will give N-butane. Isopropyl chloride in the presence of PD will give N-propane. The reduction may also be carried out by heating the alkyl halide, particularly iodides, with hydrogen iodide in the presence of red phosphorus in a sealed tube. For example, ethyl iodide plus HI in the presence of red B will give ethane and I2. Reduction through the formation of Grignard reagent. This is an indirect method of reducing alkyl halide. A solution of an alkyl halide in a dry ether is treated with magnesium to form an arterial solution of alkyl magnesium halide, commonly known as Grignard reagent. Alkyl halide plus Mg dry ester will give alkyl magnesium halide or Grignard reagent. The Grignard reagent are easily decomposed by water, providing alkanes. Grignard reagent plus HOH will give alkane and MgOHX. Methyl magnesium iodide plus HOH will give methane plus MgOHX. It may be pointed out that the alkenes and alkyl halide used for the preparation of alkene by the above mentioned methods are themselves generally obtained from alcohol, but the alcohol cannot be directly converted into alkane, as the hydroxyl group of most alcohol resists reduction to corresponding alkane. Wood's reaction. The reaction brings about the union of two alkyl radicals by the action of metallic sodium upon alkyl halide in dry ester. The resulting product are alkanes with a carbon skeleton having a higher number of carbon atoms than the reacting alkyl halide. Alkyl halide plus 2Na plus Rx in the presence of diether will give alkane and 2NAI. Methyl plus 2Na plus ICH3 in the presence of diether will give ethane plus 2NaI. Ethyl bromide plus 2NaI plus BrCH2CH3 diether will give and butane plus 2NaBr. It may be noted that when the reaction involves two molecules of the same alkyl halide, a symmetrical alkane RR having an even number of carbon atoms is formed. For preparing an unsymmetrical alkane containing 3 or more than 3 carbon atoms, for example propane, a mixture of different alkyl halide has to be used. Methyl bromide plus 2Na plus ethyl bromide in the presence of dry ether will give propane and 2NaBr. But the product obtained by using different alkyl halide constituting a mixture of alkanes which cannot be easily separated. This is because the two alkyl halide also react separately with sodium to form two more hydrocarbon as product of the side reaction. Thus, in case of above reaction, ethane from CH3Br and Na, butane from C2H5Br and Na are also obtained. The main feature of Wood's reaction is that it leads to the formation of carbon-carbon bond. As such, the reaction can be employed for preparing compounds containing higher number of carbon atom from those containing lesser number of carbon atom. For example, ethane may be obtained from methane as follows: CH4 plus Cl2 will give CH3Cl plus HCl, CH3Cl plus 2Na plus Cl, CH3 will give CH3CH3 plus 2NaCl. The order of reactivity of different alkyl halide in this reaction is iodides, then bromides, then chloride. Limitation of Wood's reaction. It is suitable for the preparation of symmetrical alkanes. It cannot be used for the preparation of methane. Third alkyl halide cannot be used in this reaction. Two mechanism has been supported for this reaction. These are intermediate formation of free radical. According to this mechanism, it is believed that the alkyl halide first form alkyl radicals which combined with one another to furnish the hydrocarbon. Thus, Rx plus Na will give R plus NaX, R plus R will give Rr. These are free radicals R and R which will give hydrocarbon. This mechanism operates when the reaction is carried out in vapor phase. Second, intermediate formation of organometallic compound. Here the reaction is believed to take place through the formation of organometallic compounds as intermediate. For example, Rx plus 2Na will give Rna plus NaX, Rna plus Xr will give Rr plus NaX. This mechanism operates when the reaction is carried out in solution. Fourth, Corey-House synthesis. This method was developed around 1970 and is a much better method than Wood's reaction for preparing alkanes containing higher number of carbon atoms than the reactant taken. It consists of a reaction between alkyl halide and lithium dialkyl copper. Alkyl halide plus lithium dialkyl copper will give alkane plus RCu plus LiX. For example, N-butyl bromide plus lithium dimethyl copper will give N-pentane and methyl copper plus LiBr. Lithium dialkyl copper required in the reaction is itself prepared from alkyl halide as illustrated below. Rx plus 2Li in the presence of dry ether will give RLi plus LiX. 2R Li plus Cux will give R2CuLi plus LiX. To obtain good yield of alkane, alkyl halide used is generally a primary alkyl halide, while the alkyl group is a lithium dialkyl copper may be primary, secondary or tertiary. An important feature of this reaction is that it can be used for the preparation of all types of alkane, whether symmetrical or unsymmetrical, whether straight chain or branch chain. Mechanism. In the beginning, the alkyl group of alkyl lithium displays halogen from copper halide to form alkyl copper RLiCux. the bond with CuX will move on X, and the bond between RLi will move on Cu, which will give RCu, that is alkyl copper plus LiX. Alkyl copper react further with alkyl lithium to form lithium dialkyl cuprate. LiR plus CuR will give R2Cu negative Li positive. Alkyl halide then undergo nucleophilic addition by dialkyl cuprate anion to generate an unstable intermediate which decomposes to form the final product. Coal-based electrolytic reaction. In this reaction, concentrated aqueous solution of sodium or potassium salt of monocarboxylic acid is subjected to electrolysis to get alkane. 2RC double bond Na plus 2H2O in electrolysis will give alkane plus 2NaOH plus H2. The reaction takes place as follows. Sodium salt of acid in equilibrium ionization will give 2RC double bond O plus 2Na. Similarly, at anode, we will get 2RC double bond O negative minus 2 electrons will give 2RC double bond O, which will give alkane plus 2CO2. At anode, 2H positive plus 2 electron will give H2. The discharge potential of H positive ion is lower than that of Na positive ion. Therefore, H positive ion are discharged at the cathode, liberating H2, while N positive ion remain in the solution. For example, sodium ethonate in equilibrium will give CH3C double bond O negative plus 2Na positive. 2CH3C double bond O negative minus 2 electron will give 2CH3C double bond O, which will give ethane plus 2 CO2H at anode, and at cathode 2H positive plus 2 electron will give H2. This is a good method for preparing ethane and higher alkane having even number of carbon atom. Methane cannot be prepared by this method. Decarboxylation of monocarboxylic acid. When heated with soda lime, sodium salt of monocarboxylic or fatty acid, usually decarboxylation or to form alkane, the reaction involves the elimination of carbon dioxide from carboxylic group. As active compounds of soda lime in this reaction is NaOH, but it is not employed as such because it melts on heating and is deliquescent as well. Sodium salt of fatty acid plus NaOH will, in the presence of CO, will give alkane plus Na2CO3, and sodium acetate plus NaOH will give methane and Na2CO3. Oakwood and CO workers 1950 have shown that the reaction proceeds according to above equation only in the case of sodium acetate. In case of higher member, various side products are also obtained. Thus, in the case of sodium propanate, the reaction gives methane, hydrogen and certain unsaturated hydrocarbons also in addition to ethane. It may be pointed out that the alkanes are also formed during some other chemical reaction, but these reactions are not employed for the actual preparation of alkane, either because of poor yield of desired products or some other drawbacks. Next is the preparation of methane. Beside methods number 2, 4, 6 described above, methane can also be prepared conventionally by dropping water over aluminium carbide. Aluminium carbide plus 12H2O will give 4AlOH thrice plus 3CH4. The gas obtained by this method is generally contaminated with hydrogen and acetylene. Preparation of ethane. Although ethane can also be prepared by any of the general method of preparation, it is generally prepared in the laboratory by reduction of ethyl iodide or ethyl bromide with nascent hydrogen produced by the action of zinc copper couple on ethyl alcohol. Ethyl alcohol plus ZnCu will give zinc ethoxide plus 2H. Ethyl iodide plus 2H will give ethane plus HI. Physical properties of alkane. Physical state. The lower members of alkane containing up to 4 carbon atoms are colorless gases. The higher normal alkanes having 5 to 7 carbon atom are colorless liquids, and beyond that they are colorless solids are at room temperature. Boiling point. The boiling point of an alkane increases regularly with increase in number of carbon atoms. There is an increase of about 20 to 34 each carbon atom added to the chain, except in the first few cases where the increase is much more. This can be explained in terms of intermolecular force of attraction. Alkanes are non-polar compounds having weak van der Waals forces of attraction between their molecule. These forces act along the surface of molecule, and their magnitude increases with increase in surface area. As the molecular size of alkane increases, the surface area and strength of van der Waals forces also increases. As a result, the boiling point also increases. Amongst the isomeric alkane, there is a small difference in the boiling point of various isomers. The branched chain isomer have invariably less boiling point than the normal compound, and the greater the branching, the lower is the boiling point of branched isomer. For instance, the boiling point of N-pentane, isopentane and neopentane are 309, 301 to 82.5 Kelvin respectively. This is due to the fact that branched isomers are more compact, that is, they have lesser surface area than their normal counterparts. Due to lesser surface area of such molecules, the van der Waals forces of attraction operating them are comparatively weaker, as such lesser energy is needed to overcome these forces for the boiling to take place, and therefore their boiling point are lower. Melting point. Melting point of alkane do not show a very smooth gradation with the increase in molecular size. For instance, let us consider the melting point of N-propane and an octane. It may be seen that the increase in melting point is much more in moving from an alkane having odder number of carbon atom to the higher alkane than in moving from an alkane having even number of carbon atom to the higher alkane. This is essentially because the intermolecular force in the crystal depend not only upon the size of molecule but also how well the molecule fit into the crystal lattice. It has been already made clear that the carbon in alkane form zigzag type of chain rather than straight chain. Now in an alkane containing an even number of carbon atom, the terminal methyl group lies on the opposite side of the zigzag chain. On the other hand, in case of an alkyl having odd number of carbon atom, the terminal methyl group lies on the side of the chain as shown below. N-hexane even number, N-heptane odd number. It appears that the alkane having odd number of carbon atom do not fit in so closely together in the crystal system as the alkane having an even number of carbon atom. As a result, the energy required to break the crystal system and thus melt the alkane is lesser in case of alkane having odd number of carbon atom. This is why they have lesser than expected melting point, as shown by only a slight increase in melting point in moving from a even number alkane to a higher odd number alkane. Specific gravity. The specific gravity of alkane also increases with increasing molecular weight but becomes constant at about 0.8. This implies that all alkanes are lighter than water. Solubility. Due to nearly same electronegativity of carbon and hydrogen atom present in them and the symmetrical shapes of their molecule, alkanes are non-polar in character. As such, they are insoluble in polar solvent such as water but dissoluble freely in non-polar solvent such as ether. The solubility decreases with increase in molecular weight. Chemical properties. The molecular structure of alkane involves only carbon-carbon and carbon-hydrogen single bond, as all these bonds are sigma bond and practically non-polar in nature. Alkane constitute a rather unstable class of compound. They are quite inert towards the common reagents such as acid, alkyls, and oxidizing or reducing agent under ordinary condition. However, under strong conditions, alkane do not undergo a few reactions, mostly involving substituent. The reaction generally takes place by free radical chain mechanism. The important reaction of alkane are described as first, halogenation. This reaction involves the replacement of one or more hydrogen atom of an alkane by a corresponding number of halogen atoms. Chlorination and bromination are carried out by treating the alkane with chlorine or bromine in the presence of light sunlight or ultraviolet light or at high temperature 525 to 673 Kelvin temperature. For example, when chlorine reacts with methane under these conditions, all the 4 hydrogen atoms of methane can be successively replaced by chlorine atom as shown below. CH4 plus Cl2 will give CH3Cl plus HCl. Similarly, CH3Cl plus Cl2 will give CH2Cl2 plus HCl. CH3Cl plus Cl2 will give CHCl3 plus HCl. CHCl3 plus Cl2 will give CCl4 plus HCl. Bromination, thorough similar to chlorination, takes place less readily. Iodination of alkane is extremely slow and reversible. CH4 plus I2 will give CH3I plus Hi, which can further give CH4 plus I2. Therefore, direct iodination of alkane cannot be brought about. However, the reaction may be carried out in the presence of an oxidizing agent such as iodic acid, nitric acid, etc., which convert the hydroxylic acid produced into iodine. 5Hi plus HiO3 will give 3I2 plus 3H2O. Fluorination of alkanes is not generally carried out because it takes place with explosive violence. Moreover, fluorination often involves extensive rupture of carbon-carbon as well as carbon-hydrogen bond. The reaction can be made less vigorous by diluting fluorine with an inert gas such as nitrogen or argon. It is obvious, therefore, that the order of reactivity of halogen towards alkane is fluorine, chlorine, bromine, iodine. Halogenation of higher alkane. Formation of isomeric halogen derivative. The halogenation of higher alkane yield a mixture of all possible isomeric halogen derivative. For example, chlorination of propane give a mixture of 1 chloropropane and 2 chloropropane. Propane plus Cl2 minus HCl will give 1 chloropropane and 2 chloropropane. Further, chlorination gives a mixture of 4 disubstituent produced, which is shown below. The mechanism of halogenation is discussed a little later. Note, it may be seen that halogenation of alkane is an oxidative process because it involves replacement of electropositive hydrogen atom by electronegative halogen atom and is accompanied by an increase in the oxidation state of carbon. Second, nitration. The process involves the substitution of a hydrogen atom of an alkane by a nitro group. It is carried out by heating the hydrocarbon in vapor state with nitric acid at about 700 Kelvin. Alkane plus HNO3 in the presence of 700 Kelvin temperature will give nitroalkane plus H2O. During nitration, Rupture of a C bond in some of the molecule also takes place. As a result, the reaction furnishes a mixture of different products. For example, the nitration of propane result in the formation of a mixture of four nitro compounds as shown below. CH3 CH2 CH3 plus HNO3 will give, in the presence of 673 Kelvin, will give 1 nitropropane and 2 nitropropane plus nitroethane and nitromethane. Sulfonation. It is the reaction involving the replacement of a hydrogen atom of an alkane by a sulfonic acid group. Only higher alkane undergoes sulfonation by reacting with fuming sulfuric acid. For example, hexane plus H2SO4 in the presence of SO3 will give hexane sulfonic acid plus H2O. Nitration and sulfonation are believed to take place by free radical mechanism. Oxidation. First, combustion. When burned in excess of air or oxygen, alkane undergo complete oxidation to produce carbon dioxide, water and large quantity of heat. CnH2n plus 2 plus O2 in excess will give NCO2 plus N plus 1 H2O plus heat. For example, CH4 plus 2 O2 will give CO2 plus 2 H2O. Delta H will be minus 890 kilojoule. 2H2H6 plus 7O2 will give 4CO2 plus 6H2O. Delta H is equal to minus 3110 kilojoule. In spite of being highly exothermic reaction, combustion require a high temperature, that of a flame, to start it. This is due to the energy of activation required to initiate the reaction. Due to the large quantity of heat produced during combustion of alkane, this reaction has tremendous practical importance. Vast quantities of hydrocarbon obtained from petroleum are used as fuel for the production of heat and power by combustion. The cooling gas, commonly known as LPG, liquefied petroleum gas, is a mixture of propane and butane compressed as liquid. Incomplete combustion of alkane due to insufficient supply of air or oxygen result in the formation of a soot or carbon black. This is used in the manufacturing of Indian ink, printer ink, black varnish, and as a filler for rubbers. Second, catalytic oxidation. When heating in the regulated supply of air or oxygen at high temperature in the presence of suitable metallic catalyst, lower alkanes are oxidized to alcohol and aldehyde, while higher homologous yield long chain fatty acid. For example, when a mixture of methane and oxygen in suitable proportion is compressed to 100 atmosphere and passed through copper tube at 475 Kelvin, methane is oxidized to methanol. 2CH4 plus O2 will give, in the presence of 475 and 100 atm pressure, will give 2CH3OH. When a mixture of methane and oxygen is passed through heated molybdenum oxide, methane is oxidized to formaldehyde. CH4 plus O2 in the presence of MO2O3 will give HCHO plus H2O. Normally, alkane resists the action of oxidizing agents such as potassium permanganate, but alkane containing tertiary hydrogen atom can be oxidized by such reagent to corresponding alcohol. For example, isobutane in the presence of alcoholic KMNO4 will give tert butyl alcohol. Fifth, thermal decomposition or pyrolysis. This process involves the decomposition of bigger molecule into a number of simple molecule by the action of heat. When heated to about 775 to 1075 Kelvin, higher alkane undergo pyrolysis to yield smaller molecule. For example, propane decomposes as follows at about 735 Kelvin. Propane in the presence of 735 Kelvin will give ethylene and methane, and in second it will give propylene plus H2 45%. It is apparent that pyrolysis involves the decomposition of carbon-carbon as well as carbon-hydrogen bond. The composition of product depend upon the nature of starting compound and condition employed. The pyrolysis or thermal decomposition of alkane observed from petroleum is commonly referred to as cracking or fragmentation. Cracking is a very important process from commercial point of view and is discussed in detail under petroleum. 6. Catalytic refining or aromatization. This process concerns the conversion of aliphatic hydrocarbon into aromatic hydrocarbon in the presence of suitable catalyst. The reaction involved dehydrogenation, cyclization and even isomerization. In some cases, it is generally carried out at a high temperature of about 720 to 280 Kelvin, high pressure 10 to 20 atm, and in the presence of a catalyst which generally consists of chromic oxide supposed on aluminium oxide. Thus, N-hexane changes into benzene and N-heptane changes into toluene. N-hexane in the presence of 770 Kelvin, 10 to 20 atm pressure, Cr2O3 or Al2O3 will give benzene plus 4H2O. N-heptane in the presence of 770 Kelvin, 10 to 20 atm pressure, Cr2O3 or Al2O3 will give toluene plus 4H2. These days, the reaction is generally carried out at 670 Kelvin in the presence of palladium as a catalyst. Therefore, the reaction is sometimes termed as platforming. Isomerization. It is the process of converting one isomer into another. It is found that when an alkane are heated in the presence of aluminium chloride and hydrogen chloride, they are converted into branched chain isomer. For example, N-hexane in the presence of 375 Kelvin and AlCl3HCl will give 2-methylpentane and 3-methylpentane. Mechanism of halogenation of alkane. Mechanism of halogenation. Halogenation of alkane is known to be a free radical chain reaction. This is because it processes through a series of steps involving free radical. Each step generally a free radical that brings about the next step till the chain of these steps is finally broken. There are three fundamental stages of chain reaction, namely chain initiation step, chain propagation step, chain termination step. Let us discuss the mechanism of halogenation by considering the chlorination of methane. First, chain initiation step. The reaction is initiated by the homolytic cleavage of a chlorine molecule into two chlorine atom or free radical, each carrying an odd or unpaired electron. The energy required for this is supplied by heat or light. Cl. There will be bond cleavage in the presence of heat or light and will give 2Cl radical. Chain propagation step. Once the chlorine atom or free radical are formed, each of them react with the methane molecule forming hydrochloric acid and generally a methyl free radical as shown in step 2. Each of the methyl radical in turn react with other chlorine molecule to form methyl chlorine and at the same time generates another chlorine atom or free radical as shown in step 3. This newly formed chlorine atom can react with another molecule of methane as shown in step 2 to produce another molecule of hydrochloric acid and another methyl free radical. The methyl free radical can again repeat the step 3 and so on. Thus, the step 2 and 3 are repeated several times and the chain gets propagated till it is ultimately terminated as shown in this figure. Chain propagation steps which are repeated several times. The chlorine atom formed in step 3 can also react with the methyl chlorine formed to yield hydrochloric acid and a new substituted methyl radical as shown in step 4. The substituted methyl radical would react with another molecule of chlorine to form dihalogenated methane as indicated in step 5. Theoretically, this process can extend further till all the replicable hydrogen atoms in the methane molecule have been substituted by chlorine. Here it is shown that further chain propagation step in case of formation of di and polyhalogenated alkanes. Chain terminating steps. The chain of reaction initiated and propagated as outlined above may be terminated if the free radical combine amongst themselves without giving rise to any new radical as shown below. Possible chain terminating steps. The chances of free radical combining amongst themselves are very low indeed because of the very small relative concentration of a free radical in the reaction mixture. Still, such a combination cannot be completely ruled out. As this happened, the chain of steps initiated by the cleavage of a particular chlorine molecule comes to an end, but other similar chain initiated by other chlorine molecule continue to operate, and therefore the overall reaction keeps on progressing. Evidence in support of the above mechanism. The free radical mechanism of halogenation is supported by the following facts. First, the reaction does not take place in dark at ordinary temperature but requires energy in the form of heat 525 to 675 Kelvin or light to initiate the process. This is because the reaction initiating step involves the dissociation of a halogen molecule into free radical which require the supply of energy. Second, high quantum yield. For each proton of energy absorbed, many thousand molecules of alkyl halide are formed. This is evidently due to the repeating chain propagation step. Third, it has been observed that addition of substances that are sources of free radical can initiate the reaction in the dark at temperature below 525 Kelvin. For example, in the presence of 0.02% of tetraethyl lead C2H54Pb, chlorination of methane proceeds in dark at 415 Kelvin. CH4 plus Cl2 415 Kelvin 0.02% C2H54Pb will give CH3Cl plus HCl. It is also known that at 415 Kelvin tetraethyl lead decomposes to give metallic lead and ethyl free radical. C2H54Pb in the presence of 415 Kelvin will give Pb plus 4 C2H5 radical. It appears quite reasonable that the ethyl radical formed in this manner attract chlorine molecule to produce chlorine atom or free radical. C2H5 plus Cl2 will give C2H5Cl plus Cl. The chlorine atom thus generated then start the chain propagation step and the reaction progresses. Similarly, the reaction proceeds at low temperature in the presence of benzyl peroxide because it generates free radical at low temperature. Fourth, role of inhibitors. An inhibitor is a substance that can slow down although stop a reaction even when present in small quantities. It has been observed that oxygen acts as an inhibitor in the halogenation of alkane. It is believed that to be due to the fact that an oxygen molecule combines rapidly with an alkyl radical to form the comparatively much less reactive peroxide alkyl radical R double bond O. R plus O2 will give ROO. As the new radical cannot continue the chain get terminated. Thus each oxygen molecule breaks a chain by combining with an alkyl radical and thus stop the formation of thousands of molecules of alkyl halide. This naturally stop downs the rate of reaction. Of course, when all the oxygen molecules have been used up, the reaction proceeds normally. Some important aspects of halogenation of alkanes. We will now discuss some important and interesting aspects of halogenation of alkanes. First, relative reactivity of halogens in halogenation of alkane. The order of reactivity of halogens in various halogenation reaction of alkanes have been found to be F2Cl2Br2I2. In fact, in case of iodine, the reaction does not seem to take place at all. We would try to account for this observed order of reactivity by considering the energy change during the chain initiation and propagation step in the reaction of a particular alkane, say methane, with different halogen. Since energy of activation has not been measured for the various steps of all the reaction, the value of delta H for different steps derived from the bond dissociation energy would be of a lot of help to us. The value of delta H for each of the three most important steps during halogenation of methane with different halogen are given below. Second, termination state for halogenation. It has been already stated that the vital step in the halogenation of alkanes is RH plus X radical will give RH plus HX. The energy of activation for this step, which controls the overall process, is obviously equal to the difference in energy between reactant and termination state. Let us have a look at this transition state, the formation of which is so important for the progress of halogenation. In this termination state, the carbon hydrogen bond of the alkane is somewhat stretched but not completely broken, while a new hydrogen halogen bond have been partially formed. At the same time, the odd electron which is on halogen is in case of reactant and on alkyl group in case of product is divided between the two in the transition state. For depicting such a state, dotted line may be used for indicating partially broken and partially formed bond, while the symbol partially may be employed for representing each atom share of odd electron as shown below. Reactant Rx plus X radical will give RHX. This is transition state will give R radical plus HX. The transition state leading to the formation of a particular free radical has some of the properties of that free radical. Thus, the free radical and the corresponding transition state have the same order of stability and ease of formation. Relative reactivity of alkane in halogenation and relative reactivity of different classes of hydrogen atom. If a mixture of equimolar amount of two or more alkane is allowed to react with a limited quantity of chlorine or bromine, the product obtained consists of a mixture of different alkyl halide corresponding to the alkane taken, but the relative quantities of alkyl halide in the mixture are not the same. This means that different alkanes exhibit different degree of reactivity while reacting with a particular halogen. These relative reactivities of alkane can be attributed to the reactivity of different classes of halogen atom present in them. It has been found that irrespective of the alkane in which they are present, the relative reactivity of hydrogen follows the order tertiary, secondary, primary. The hydrogen of methane being lesser reactive than even prime hydrogen. To have an idea of the magnitude of difference in the relativity of different hydrogen atom, let us consider the reaction between a mixture of equimolar amount of ethane and methane and a small quantity of chlorine at 298 Kelvin in the presence of light. It is found that the amount of ethyl chloride formed is about 400 times as much as that of methyl chloride, as shown in this reaction. This means that ethane is 400 times as reactive as methane, allowing for the fact that ethane contains 6 hydrogen atoms while methane has only 4. Each primary hydrogen of ethane is still about 267 times, that is 400 into 4 by 6 as reactive as each hydrogen of methane. The relative reactivity of different classes of hydrogen atom may be explained by considering the relative stability of alkyl radical formed in the step which control the overall process of halogenation. For instance, in case of chlorination of methane and ethane, the relative rate of controlling step may be written as CH4 plus Cl radical will give CH3 radical plus HCl, CH3 CH3 plus Cl radical will give CH3 CH2 radical plus HCl. Fourth, orientation of halogenation. It has been observed that sometimes a compound can form different products on reaction with the same reagent. This means that the compound has more than one reactive sites where the extract by the given reagent can takes place. The process of determining the particular site or sites in the molecule where the reaction is more likely to occur is known as orientation. It involves the examination of factors which can influence the relative rate of completing reactant. For the present, let us consider the orientation of halogenation of alkane. It has been pointed out earlier that the halogenation of a highly alkane can lead to the formation of two or more isomeric products. For instance, the chlorination of propane at room temperature produces a mixture of N-propyl chloride and isopropyl chloride in ratio 45:55. The rate controlling step for the two completely reaction involve the formation of N-propyl and isopropyl radicals by the abstraction of primary and secondary hydrogen of propane as shown below. CH3 CH2 CH3 plus Cl radical will give CH3 CH2 CH2 radical plus HCl and CH3 CH radical CH3 plus HCl. Naturally, the relative quantities of the two halides produced would depend upon the relative rate at which N-propyl and isopropyl radical are formed. Let us relativity and selectivity. Chlorination versus bromination. It has been studied earlier that in the halogenation reaction of alkane, chlorine is more reactive than bromine. It has been discussed in case of alkane containing different types of hydrogen atom, the ease of abstraction or reactivity of different type of hydrogen follows the order tertiary, secondary, primary, irrespective of the nature of halogen taking place in the reaction. But now we consider a very interesting observation with the help of a simple example. When propane is subjected to chlorination, N-propyl chloride and isopropyl chloride are formed in ratio 45:55. But when propane undergoes bromination, N-propyl bromide and isopropyl bromide are formed in ratio 4:96, keeping in view the number of primary and secondary hydrogen 6 and 2 respectively, it is clear that secondary hydrogen of propane are more reactive than the primary hydrogen in both the cases. But there is much more selective abstraction of secondary halogen in bromination than in chlorination. In general, the relative rate of abstraction of tertiary, secondary, and primary hydrogen of alkane in chlorination at room temperature are 5 ratio 38 3.8 ratio 1, while in bromination at 400 Kelvin the relative rate are 1600 ratio 82 ratio 1. This means that bromination is less reactive more react but more selective in its reaction with different types of hydrogens. On the other hand, chlorine is more reactive but less selective. This is the accordance with the relatively selectivity principle, according to which if the attracting species is more reactive, it will be less selective, while a less reactive species is more selective. To understand the above principle, let us consider the transition state involved in the rate controlling step, that is attack of halogen free radical on alkane of chlorination and bromination of alkane. The reaction of highly relative chlorine atom with alkane has very low E activation, and therefore the transition state is reached quite easy when the alkyl radical character has just started developing. Therefore, the stability of alkyl radical ultimately form does not have much effect on the ease of occurrence of the reaction. RH plus Cl radical highly reactive, it will give HCl, which is the transition state, reacted quite easily. Alkyl radical character just beginning to develop will give R radical plus HCl. In case of much less reactive bromine atom, the above step involved high activation energy, as such transition state is reached very late when sufficient alkyl radical character have already developed. Therefore, the transition state resemble the ultimately formed free radical in its stability and ease of formation, that is tertiary, secondary, than primary. RH plus Br radical low reactivity will give reacted quite late alkyl radical character sufficiently developed. This is the transition state which will further give R radical plus HBr. In other words, bromine atom which attack the tertiary hydrogen relatively much more easily than secondly, which in turns would be attacked more easily than primary hydrogen. Hence, as compared with more reactive chlorine, there will be much more selectivity in the reaction with less reactive bromine. So, our chapter is completed. Thank you.